Few places on Earth expose the planet's internal mechanics with such brutal clarity as the Almannagjá Rift in southwestern Iceland. The fracture cuts across the landscape like a wound that never fully heals, a visible reminder that continents are not fixed masses but moving pieces of a restless crust. Tourists walk along its walls every year, cameras raised toward cliffs of volcanic basalt, often unaware that the crack beneath their feet exists because two enormous tectonic plates are actively pulling apart. The separation is slow enough to escape human senses, yet powerful enough to reshape entire regions over geological time. How dangerous can a crack in the Earth truly become when it marks the boundary between continents? How does a fracture remain stable for centuries while simultaneously expanding toward an uncertain future? And what happens when volcanic pressure, seismic activity, groundwater, and tectonic stress converge in one of the most geologically active regions on the planet? The Almannagjá Rift lies within Thingvellir, a valley positioned directly on the mid-Atlantic ridge, the immense submarine mountain chain where the North American plate and Eurasian plate diverge. Most of that ridge remains hidden beneath the Atlantic Ocean, but Iceland rises above sea level because volcanic activity continuously supplies magma from below. This makes Iceland one of the very few locations on Earth where a person can stand between tectonic plates and physically observe continental drift in progress. At Almannagjá, the widening boundary manifests not as a single clean fracture but as a system of faults, fissures, lava formations, and collapse blocks that together reveal the dynamic behavior of the crust. The scale of the geological forces involved becomes difficult to comprehend when viewed only from the valley floor. The North American plate moves generally westward, while the Eurasian plate shifts eastward. Their average separation rate measures roughly nearly 1 inch per year, approximately 2½ centimeters annually. That movement may appear insignificant within a human lifetime, yet over thousands of years it accumulates into dramatic structural change. Valleys widen, cliffs collapse, lava fields fracture, and groundwater systems reorganize. The Almannagjá Rift exists because the crust cannot stretch indefinitely without breaking. As tension builds, the brittle upper layers fracture repeatedly, producing long fault scarps and grabens where land between faults subsides relative to surrounding terrain. The cliffs lining Almannagjá consist largely of basalt, the dark volcanic rock created when fluid lava cools rapidly near the surface. Iceland's volcanic origins dominate every aspect of the rift's structure. Roughly 10,000 years ago, after the retreat of glaciers from the last ice age, massive eruptions flooded the area with lava. Subsequent tectonic stretching fractured those solidified lava plains. Repeated seismic episodes widened existing cracks and created new ones. The result is not a static canyon carved by water erosion, but an actively evolving tectonic landscape shaped primarily by crustal extension. Unlike dramatic cinematic depictions of earthquakes splitting the ground open within seconds, continental rifting usually unfolds incrementally. Most of the time, the movement remains imperceptible. Stress accumulates silently in the crust until faults suddenly slip during earthquakes. Even moderate seismic events can shift sections of land by several feet or more than 1 meter in moments. Iceland experiences thousands of earthquakes each year because the island straddles this tectonic boundary. Many are too small for people to notice, but larger swarms periodically reveal the immense strain beneath the surface. Almannagjá's danger does not stem from a single catastrophic scenario. The hazard comes from the combination of tectonic instability, volcanic systems, rockfall potential, groundwater interactions, and Iceland's position above an active mantle plume. The rift represents a visible symptom of a deeper geodynamic engine operating continuously beneath the island. The mantle plume beneath Iceland supplies unusually high volumes of magma from deep within Earth's interior. As hot material rises, pressure decreases, allowing partial melting of mantle rock. That magma feeds Iceland's volcanic systems while simultaneously weakening and uplifting the crust. The interaction between the mantle plume and the mid-Atlantic ridge intensifies geological activity beyond what would normally occur at a divergent plate boundary alone. Without this plume, Iceland likely would not exist above sea level. The volcanic history surrounding Almannagjá demonstrates how closely linked tectonic extension and magma intrusion truly are. When magma forces its way upward into fractures, it can pry the crust apart. Long vertical intrusions known as dikes inject molten rock into weaknesses within the crust, sometimes triggering extensive earthquake sequences. During major rifting episodes elsewhere in Iceland, ground deformation has widened fissures by several yards and several meters over short periods. Entire landscapes have shifted as magma migrated underground. Although Almannagjá itself currently appears stable compared with Iceland's more eruptive zones, the region remains part of an interconnected tectonic system. Geological calm in Iceland rarely represents permanence. Strain accumulation continues whether visible or not. The walls of the rift reveal evidence of repeated fault motion through stacked lava flows offset against one another. In some sections, cliffs rise approximately 100 feet to 130 feet high, roughly 30 to 40 meters. These escarpments formed as land subsided along normal faults created by crustal extension. The valley floor between them gradually dropped while adjacent blocks remained elevated. Every major tectonic episode enlarged the displacement. Water further complicates the rift's geology. Iceland's volcanic rocks are highly porous, allowing groundwater to move efficiently through fractures and lava layers. Meltwater and precipitation infiltrate deep into the subsurface, feeding springs and underground reservoirs. Thingvellir famous clear waters owe their purity partly to natural filtration through volcanic rock over long periods. Yet water moving through fractures also contributes to mechanical and chemical weathering. Freeze-thaw cycles during winter widen cracks as expanding ice exerts pressure on rock walls. Over time, this destabilizes cliffs and increases the likelihood of rockfalls. Rockfall hazards remain significant throughout Icelandic rift landscapes. Basalt cliffs fractured by tectonic stress often contain unstable columns separated by joints and fissures. Earthquakes can loosen already weakened sections, causing sudden collapses. Even smaller fragments pose danger to visitors traversing narrow paths near cliff bases. The geological beauty attracting tourists is inseparable from the instability that created it. Historical records and geological evidence indicate that Iceland periodically undergoes major rifting episodes involving coordinated seismic and volcanic activity across large regions. One of the most significant modern examples occurred during the Krafla fires between the mid-1970s and mid-1980s in northern Iceland. During that period, repeated magma intrusions and eruptions accompanied extensive crustal deformation. Ground fissures widened, faults shifted, and the landscape changed measurably. Though distant from Almannagjá, the events demonstrated how rapidly Icelandic rift systems can awaken after long quiet intervals. The island's geological history contains even more violent examples. Massive fissure eruptions, such as the Laki event in the late 18th century, released enormous volumes of lava and volcanic gases. While Laki occurred in southeastern Iceland rather than Thingvellir, it illustrated the destructive potential inherent within Iceland's tectonic framework. Lava flooded vast areas while sulfur-rich emissions disrupted climate and agriculture across Europe. Such eruptions emerged from the same underlying tectono-magmatic processes responsible for the fractures visible at Almannagjá. The rift's location also carries historical significance unrelated to geology yet deeply influenced by it. Thingvellir became the meeting site of Iceland's early parliament more than 1,000 years ago, partly because the valley provided accessible open terrain within a rugged volcanic landscape. The dramatic cliffs and fissures served as natural boundaries and landmarks. Human history there unfolded directly atop an active plate boundary, linking governance and geology in unusual fashion. Modern monitoring technology has transformed scientific understanding of Iceland's crustal dynamics. High-precision global positioning system measurements track plate motion down to fractions of an inch in millimeters annually. Satellite radar interferometry detects subtle ground deformation across volcanic and tectonic zones. Seismic networks record earthquake swarms that may indicate magma movement deep underground. Together, these tools reveal a crust in constant motion. Data from Iceland consistently confirm that plate separation does not occur evenly across the island. Instead, strain concentrates within volcanic rift zones several miles and kilometers wide. These zones migrate gradually over geological time as magma pathways evolve. Faults become active, then dormant, while new fractures emerge elsewhere. Almannagjá represents only one exposed segment of a far broader tectonic architecture. One reason the rift commands such attention is its accessibility. Many tectonic boundaries remain hidden beneath oceans or remote mountain ranges. At Almannagjá, visitors can walk directly through the fissure system. The ease of access creates a powerful visual impression but can also obscure the immense timescales involved. The valley did not form from a single earthquake or eruption. It emerged through countless episodes of extension, subsidence, faulting, and volcanic resurfacing spanning thousands of years. The geometry of the rift reflects the mechanics of brittle deformation. As the crust stretches, fractures propagate downward and outward. Blocks bounded by faults rotate and subside. Some fissures remain narrow while others widen into substantial canyons. Secondary cracks branch outward from primary faults, producing complex networks across lava plains. Beneath the surface, magma intrusions exploit these weaknesses, reinforcing patterns of extension. The basalt composing the cliffs often cools into polygonal columns due to contraction during solidification. These columnar structures create striking visual patterns but also influence mechanical behavior. Vertical joints can act as planes of weakness, increasing susceptibility to collapse during seismic shaking or freeze-thaw expansion. Engineers and geologists monitoring visitor safety in Icelandic rift environments must account for these natural fracture systems. Climate influences the evolution of the rift as well. Iceland's glaciers, although distant from Thingvellir itself, have historically affected crustal stress through loading and unloading processes. During the last ice age, thick ice sheets depressed the crust beneath their immense weight. As glaciers melted, the land rebounded upward. That rebound altered regional stress fields and may have influenced fault activity and magma generation. Some research suggests deglaciation can increase volcanic productivity by reducing pressure on underlying mantle material. The interaction between fire and ice remains central to Icelandic geology. Subglacial eruptions elsewhere on the island demonstrate how magma encountering ice can trigger explosive fragmentation, rapid melting, and catastrophic floods known as Jökullaups. Although Almannagjá is not directly beneath modern glaciers, it exists within a geological system repeatedly shaped by glacial cycles and volcanic heat. Earthquake swarms near Iceland often reveal the migration of magma through crustal fractures. Instead of isolated single events, the island frequently experiences sequences involving hundreds or thousands of tremors over days or weeks. These swarms occur because moving magma stresses surrounding rock, causing numerous small failures. In some cases, eruptions follow, in others, magma stalls underground. The uncertainty surrounding such sequences complicates hazard forecasting. The visibility of tectonic extension at Almannagjá sometimes leads to misconceptions about continental drift occurring as a smooth opening crack. In reality, plate motion distributes across many faults and fractures. Some sections remain inactive for long periods while adjacent zones accommodate most movement. Stress transfer between faults can reactivate older fractures unexpectedly. Geological systems rarely behave with perfect symmetry or predictability. The rift's submerged sections add another layer of complexity. Clear groundwater-filled fissures within the Thingvellir region connect to extensive subterranean pathways through fractured basalt. Divers exploring these fissures encounter extraordinary visibility due to the filtration properties of volcanic rock. Yet the underwater environment also highlights how interconnected Iceland's hydrology and tectonics truly are. Fractures controlling groundwater flow today may widen or shift during future tectonic events. The broader mid-Atlantic ridge stretches more than 10,000 miles and 16,000 kilometers through the Atlantic Ocean, representing one of Earth's largest tectonic features. Most of it remains hidden beneath several thousand feet and meters of seawater. Iceland offers a rare exposed cross-section of ridge processes normally inaccessible without deep ocean exploration. Almannagjá therefore functions as both a local geological hazard and a globally important natural laboratory for understanding plate tectonics. Before the development of plate tectonic theory during the 20th century, the origins of features like Almannagjá remained poorly understood. Earlier explanations often focus solely on volcanism or localized subsidence. The recognition that Earth's lithosphere consists of moving plates transformed interpretation of Icelandic geology. Rift valleys, volcanic alignments, and earthquake distributions suddenly fit within a coherent global framework, linking seafloor spreading, mantle convection, and continental motion. Despite advances in monitoring and theory, significant uncertainties remain regarding how rift systems evolve over long timescales. Some continental rifts eventually widen into new oceans, as occurred during the breakup of ancient supercontinents. Others fail before complete separation occurs. Iceland occupies an intermediate environment where oceanic spreading intersects a mantle plume above sea level. Whether future tectonic evolution will maintain Iceland as a volcanic island or fragment, it further remains tied to deep mantle processes unfolding over millions of years. The danger associated with Almannagjá also arises from human perception. Geological change occurring slowly can appear harmless, precisely because it lacks immediate visibility. Visitors walking through the rift may interpret the landscape as ancient and static, rather than active and evolving. Yet Iceland repeatedly demonstrates how quickly dormant systems can reactivate. Earthquake swarms emerge with little warning. New fissures open across roads and fields. Lava eruptions begin after centuries of quiet. In recent years, the Reykjanes Peninsula southwest of Reykjavik has illustrated this volatility dramatically. After centuries of relative inactivity, the peninsula entered a renewed phase of seismic and volcanic unrest. Repeated magma intrusions, fissure eruptions, and intense earthquake swarms transformed populated areas and infrastructure. Although separate from Thingvellir, the activity underscored the persistent tectonic energy operating across southwestern Iceland. The mechanics driving these events connect directly to the same plate boundary expressed at Almannagjá. Crustal extension creates space. Magma rises to fill that space. Faults adjust as stress redistributes. Over time, the process constructs new crust while tearing older crust apart. Iceland simultaneously grows and fractures. The cliffs at Almannagjá preserve this history layer by layer. Each lava flow records an eruption. Each offset marks fault displacement. Each fissure reflects accumulated tension. The landscape serves as an archive of repeated geological episodes extending back thousands of years. Reading that archive requires understanding the interplay between volcanism, tectonics, hydrology, climate, and time. Even the shape of the valley floor reflects tectonic structure. Depressed grabens form where central blocks drop between parallel faults. Some sections contain relatively flat surfaces produced by lava infill or sediment accumulation following subsidence. Elsewhere, irregular fracture patterns dominate. The apparent order of the landscape conceals a long sequence of overlapping geological events. The rift's continuing evolution means the present landscape represents only a temporary stage. Future earthquakes may deepen existing fissures or create new ones. Eruptions elsewhere in Iceland could alter regional stress fields. Climatic changes may influence erosion and groundwater circulation. Over thousands of years, the valley will continue widening as plates diverge. One of the most striking aspects of Almannagjá is the contrast between the slow pace of tectonic motion and the immense cumulative consequences of that motion. At approximately 2½ centimeters, or nearly 1 inch annually, plate separation seems trivial. Yet over 1 million years, that rate amounts to roughly 15½ miles or 25 kilometers of displacement. Geological time transforms imperceptible annual changes into continental-scale restructuring. Iceland's infrastructure increasingly intersects with these geological realities. Roads, pipelines, geothermal facilities, and tourism networks all occupy terrain shaped by active tectonics. Managing risk requires continuous monitoring and adaptation. Even areas considered relatively stable remain subject to long-term crustal deformation. Geothermal activity throughout Iceland further reflects the high heat flow associated with the plate boundary and mantle plume. Hot water systems circulate through fractures and porous volcanic rock, providing renewable energy resources that power much of the country. Yet those same geothermal systems depend upon the underlying tectonic and magmatic environment that also produces earthquakes and eruptions. Iceland's prosperity is intimately connected to the geological forces that threaten it. Geophysical studies indicate that Icelandic crust differs significantly from typical oceanic crust because of the mantle plume's influence. The crust beneath parts of Iceland can reach thicknesses far greater than ordinary mid-ocean ridges. This additional thickness affects how stress distributes, how magma rises, and how faults develop. Almannagjá therefore reflects geological conditions not perfectly replicated elsewhere on Earth. The region's seismicity also demonstrates the relationship between tectonic and volcanic processes. Some earthquakes result primarily from fault slip due to plate motion. Others occur because magma movement changes pressure conditions underground. Distinguishing between the two can prove challenging during active unrest. Clusters of small earthquakes sometimes precede eruptions, but not always. Predicting precisely when or where magma will breach the surface remains difficult despite sophisticated monitoring. Over long periods, repeated eruptions can bury older fault systems beneath fresh lava while new fractures form above them. This recycling continually reshapes Iceland's surface geology. Almannagjá's current appearance therefore represents only the latest configuration within an evolving volcanic rift environment. The role of erosion, though secondary to tectonics in forming the rift, remains important in modifying it. Wind, precipitation, freeze-thaw weathering, and water flow gradually alter cliff faces and transport sediment into lower areas. Over centuries, these processes soften some features while exposing others. Yet tectonic activity repeatedly rejuvenates relief by creating fresh scarps and fractures.